First, I would like to thank organizers that they invited me here. It's my first time in Korea, my first time in Asian continent, actually, and I like it very much, so thank you very much for inviting me. Today I would like to tell you something about para-CR structures, which I call them, and differential equations. Before saying something about para-CR structures and differential equations, I just recall what a CR structure is, just to make comparison with this para-CR business. So a CR structure is a triple MHJ, where H is a subbundle of the tangent bundle, and J is linear operator from H to H, such that J squared is minus identity, and some compatibility, integrability conditions are needed to define CR structure. So this, having this J in H, we go to the complexification, we extend it to the complexification, and we have a split of these things onto plus I, minus I eigenspaces. And now this triple is called CR structure, provided that any commutator of any two sections of this thing just sits in there. Okay. So the thing which is needed because of having this J is that rank of this H is just 2R R plus R. Okay. And then if the dimension of manifold is K plus 2R, then such CR structure, I will call it CR structure of type KRR. Okay. So what is a para-CR structure for me? So essentially what I want to change here, I want to change this J to be squared, not to minus identity, but to plus identity. So I consider now M is H and linear operator K, such that H is here, and we have J, K from H to H linear, such that K squared is now identity on H. Okay. So now there is the first difference between this situation. Here, if we just look for the eigenspaces of this K, we have to go to the complexification. Here we don't need to go to complexification. So now we have H splits on plus and H minus, which these guys are plus 1 and minus 1 eigenspaces for K. So it is not anymore needed that the rank of this bundle be even, and now I can have that rank of H plus is R, rank of H minus is S, and of course I need this sort of integrability conditions, which now to split onto two different ones, I need that this guy is integrable and this guy separately is integrable. And now such thing I will call para-CR structure of type KRS, where dimension of M is K plus 1. Okay? So this K here is called codimension, likewise here. And there are these two spaces, H plus and H minus, with respective dimension R and S. So examples of, guys, the simplest examples of CR structures are just real hypersurfaces in Cn. So we just have a real hypersurface in Cn. We have immediately a CR structure of type 1 of 1 n minus 1 n minus 1 in this terminology. So remembering that examples of CR structures can be obtained as real hypersurfaces in Cn, one can think about simplest examples here to just consider hypersurfaces in examples. Hypersurfaces in R some n plus some other n. Okay, so we just now have, like here we had Cn, which was now we have Rn plus Cartesian product with Rn. So why when I heard about these structures some years ago from Dmitry Alexievsky, and when I heard it from him, I was thinking that this is natural, that these guys have natural applications in the theory of differential equations whose solution space depends on finite number of parameters, especially ODEs. So let me explain this.
Don't you assume some non-generality condition? That means
I will assume some genericity condition here for the hypersurface.
That means the bracket of H plus and the H minus.
No, I don't assume anything more than these two integrability conditions. So essentially, I have two foliations, right?
Only integrability.
Right, only integrability. So let me give you an example how these kind of structures appear in the theory of ODEs. So consider a simple or general nth order ODE. Like this, and consider its general solution. Of this stone is y is function of x and n constants of integration. So therefore, such general solution of such equation can be considered as hypersurface. So this defines a hypersurface sigma in R2 plus n with coordinates x, y, a0, a n minus 1, which is defined by such that psi of x, capital psi x, y, and ai's is 0, where this capital psi is just y minus, let me call this solution is small psi, yeah? So now, given a general solution of an ODE, of a general ODE, I have a hypersurface in this R2 plus n, and this hypersurface acquires naturally for a CR structure from the ambient space R2 plus n. So let me show you how to get it. We first have this 2 plus n and some linear operator from R2 plus n to R2 linear such that k square is equal identity, kappa square is identity, and such that its plus positive eigenvalues are given by these two guys, and negative eigenvalues, eigenspaces are just these guys. Okay, so given in R2 plus n such kappa, this gives me the split of this R2 plus n onto R2 cross Rn, and the split is given, the operator is defined in this way, and now this thing defines a para CR structure of type 1, 1, and minus 1 on sigma in the following way. So the problem is how to define this bundle H. So you just define H like in CR case, that you define H at point P to be intersection of kappa times tangent space at P with the tangent space, and this therefore defines me an operator K from HP to HP, such that this K, when I restrict kappa to this HP, then there will be K, so kappa restricted to HP is my K at P, and this K gives me a para-CR structure. Explicitly, I just see that my tangent space is just given spanned by vectors which I call X, Y1, Y2, Yn minus 1, and Z, where X is just psi of X, capital psi sub X dy minus capital psi over y dx. Y1 is just psi 1 d0 minus psi 0 d1, where this subscript is the derivative with respect of this a0, a1, a2, an minus 1. So psi sub 1 means that this derivative of psi with respect to a0, I mean of this psi. Then y2 is just psi 2 d1 minus psi 1 d2. Then y n minus 1 is just equal to psi n minus 1 n minus 2 minus psi n minus 2 dn minus 1, and finally z is just psi 0 dy minus psi y d0. And now, because my kappa is defined in such a way, you see that this thing has eigenvalues plus 1 of this k. This thing has eigenvalues minus 1. And this thing is just beyond kappa, k. When k is applied on this, just this goes away from the thing. So that this space is just therefore my h plus. This space is just h minus, and I have here one guy, and here I have n minus 1. So my codimension is 1. The R thing is 1. S thing is n minus 1. So such solution of a general solution of nth order ODE defines me a para-CR structure of type 1, 1, and minus 1. Now, if I have para-CR structures, I can consider these para-CR structures modulo para-CR equivalence. So what would be the para-CR equivalence of two para-CR structures? You need a diffeomorph. So if you have M, H, and K, and M prime, H prime, K prime, you are looking for a diffeomorphism, perhaps local, from M to M prime, such that it just pushes pushes forward h to h prime and k to k prime. And the now suppose that you have an equation. So what you see in this picture is that now you can consider the ferromorphism of this R2 plus n that preserve the split R2 plus n onto R2 across Rn. This diffeomorphism from the point of view of differential equation is just point transformation of the variables. You just can mix, because these two corresponds to x and y. So it tells you that you can just mix x and y variables. And of course you can always, given an equation, you can always mix the constant of integrations, which are represented by this a0, n minus 1. So therefore, the change of the, if you just consider a contant equivalent equation to this one, then you get its corresponding general solution. You go through this procedure, and you get another para-CR structure of type 1, 1, and minus 1. And because of this comment that I just made in a second ago, it means that that such nth order ODE considered modulo point transformations of variables is just defining uniquely this para-CR structure. So para-CR structure of type 1, 1, and minus 1, examples of such para-CR structures are just given by nth order ODEs modulo point transformations of variables. Right.
Instead of working on the space of initial conditions A's, could you reformulate this?
Yes, I will do it.
Oh, sorry.
I will do it. Right. But this I wanted to start like this because it is very much in the spirit of this how CR structures appeared in Cartan. CR structures appear at just hypersurfaces in CN. So I just wanted to give an example of this sort. But I'm passing slowly to the interpretation in terms of jets. Okay. So the conclusion of this starting point is that nth order ODE true. Okay, nth order ODE considered modulo point transformations of variables give rise to para-CR structure of type 1, 1, and minus 1. Okay. So now I slowly want to approach this question of Ian. So to do this, I just reformulate my definition of para-CR structure in local language, like Cartan was doing for hypersurfaces in CN. So now let me pass the para-CR a la Cartan. Okay. So this para-CR structure is defined in terms of M, H, and K, but from this what is said here is essentially equivalent to this that we have just M and two distributions, one of rank R, the other of rank S, and these two distributions are integrable. So we have the following: given a para-CR of type R, K, R, S, we just have this thing, and now we pass from H plus and H minus to its annihilators. Work in terms of annihilators. And now so this para-CR structure I consider here is of type Chi, K, R, S. So now I consider annihilators. So span of K forms lambda 1 to lambda K, which is annihilator of H plus H minus, which is my entire H. So first I look for annihilator of H, and this defines me some some one forms lambda 1, lambda k. They are not uniquely defined, but I can just have k linearly independent one forms at each point that annihilate h, so I could call them lambda 1. Then span of lambda 1, lambda k, mu 1 to mu r, there will be annihilator of h minus, and finally span of lambda 1, lambda k, mu 1 of mu s will be annihilator of h plus, right? So now, as I said, these forms are defined by my para-CR structure not uniquely. They are defined up to some freedom, so the coframe on M, given in terms of forms lambda, forms mu, and forms nu, is given up to the following transformation. I can just replace my lambda with lambda, each lambda, by some matrix which just mixes all lambdas with themselves. I can replace my mu's by some matrix that mixes mu's and can add some piece of lambda. And finally, I can replace my nu's by some matrix that mixes nu's. And I can, of course, still add some of lambdas. Okay? So, in other words, given a para-CR structure of type KRS, I have a class of one forms on M, which are linearly at each point, linearly independent at each point, and they are given modulo this transformation where the functions aij, fba, h beta alpha, and this bj a and cj alpha are some functions on M such that determinant of matrix A times determinant of matrix F times determinant of matrix H is non-zero at each point. Okay? So, in other words, I can totally reformulate my definition of para-CR structure locally in the following way, that a para-CR structure on K plus R plus S dimensional manifold is a manifold M with class of one forms like this, which are linearly independent at each point, and they are given modulo these transformations. Okay? So that's not the end of the story. So this thing only encapsulates everything up to here in my definition. In my definition, I need to add the integrability conditions here, and these integrability conditions plus integrability conditions, which in language of my one forms in the following, that d lambda I lambda 1 wedge lambda k wedge mu 1 wedge mu r must be 0, d mu a wedge lambda 1 wedge lambda k wedge mu 1 mu r must be 0. So this thing essentially encapsulates the, so these guys were annihilators of H minus. So in other words, these equations assure these integrability conditions, and there is another one for the mu forms. So d lambda I lambda nu 1 nu s equals 0, and d nu alpha lambda nu s equals 0. Okay? So that's my entire definition of my para-CR structure in terms of these forms lambda. So there's a manifold with a coframe given modulo these transformations, and this coframe satisfies these integrability conditions. That's now I can just introduce some local coordinate system that will just give me some canonical way of, not canonical way, but a way of expressing these para-CR structures locally.
Is given ODE analytic one? Is F analytic?
Which one? This F,
ODE.
this F here? Not necessarily, not yet. But I a bit drifted from the case of a given ODE. Now I'm just speaking about general para-CR, but in a moment I will just return to my example, okay? So now I can apply Frobenius theorem. I was told that Frobenius is without moment. Frobenius theorem, which can be applied to this thing, and Frobenius theorem tells me that the para-CR structure lambda I mu A mu alpha locally defines two partially two coordinate systems in which forms some representatives of these forms lambda mu can be written as, and so either there is coordinate system which I called yxa, and then lambda I just can be written in the form mu A can be just this, and mu alpha is equal like this. So, and L is some matrix, some functions which depends on all the coordinates which are x, actually y, x, and a. So that's the first coordinate system, or there is another one which I call y bar plus, now there is here L bar alpha I d a alpha mu a dxa mu alpha dA alpha, where this function, these functions depend on all the coordinates which is x, y, and a. So this immediate application of the Frobenius theorem, the first two equations gives me y and x. So the first equation tells me about these two collections of functions x and y, such that lambda is like this, mu is like that. The other part tells me that there is connection of these y bars and a's, such that lambda is like this and mu is like that. But now mu, now I can take lambda from here, mu from here, and mu from here, and then I see that I have actually two coordinate systems. One in one of these coordinate systems, which is x, y, a, I can write my forms like this, this, and they represent the same class here. In the other coordinate system, I can write them like that. I'm talking about this. I will need this in the future. In particular, for 1, n minus 1, I can use, for example, this representation. So for 1, n minus 1, I will have only one form lambda. So this lambda will be only, therefore there will be only y, only one y and yx here, and then I can write this lambda as dy minus p dx, and mu as dx, and nu1 up to nu n minus 1 as dA1 up to dA n minus 1. So that's the first thing. So given a para-CR structure of type 1, 1, n minus 1, I can always locally find a coordinate system in such a way that this para-CR structure is represented by lambda, mu, and nu given by this thing. Okay? There is a simple application of this thing. If you come from CR structure theory, you know that in CR structure theory there is this very subtle business about local embeddability of an abstractly defined CR structure. You have abstractly defined CR structure, and you are asking if this abstractly defined CR structure, for example, of hypersurface type, can be locally embedded in Cn in such a way that the structure that comes from the ambient space is precisely the equivalent to the one. And in the case of CR structures, such embedding, even locally, not always exists if the starting abstract CR structure is only smooth and not real analytic. But here, actually, this representation like this and representation like this very quickly shows that you always can locally embed a para-CR structure of type KRS. So that was just an aside. That is not the main point of my talk. I want to now pass to the equations.
But can you write it from some ODE like you explained?
Yes, that's what I'm trying to. That's what I'm trying to do now. So now, the first thing is that I can always embed, but it is not relevant for this what I want to tell in the future. So now let me start with ODEs once again, and now I will try to satisfy Ian Anderson. So ODEs once again. There's another way of defining para-CR structure for ODEs via this approach that Ian wanted. So now I start with my ODE like this. And I now define a para-CR structure on the jet space by means of the contact forms. So I will just define my lambda, given such an equation. I define my lambda as dy minus y dx. I define my mu as dx. I define my mu1 by dy minus y2 dx. Mu n minus 2 as dy n minus 2 minus y n minus 1 dx. And finally, mu n minus 1 by dy n minus 1 minus f of x, y, y1, yn minus 1. Okay? So given an equation, I define my forms lambda, mu, nu1 up to nu n minus 1 in this way. And now I say that this gives me a para-CR structure because I just consider entire class generated by these forms, like here. Okay? So this sort of structure I will be, so this defines and now extend lambda, mu, and nu to a class lambda, nu via this thing. And you will get a para-CR structure of type 1, 1, n minus 1, which I will call canonical para-CR structure associated with nth order ODE. Okay? So now the key question is Vicente's question. Is every para-CR of type 1, 1, n minus 1 para-CR equivalent to a para-CR to a canonical para-CR of some nth order ODE? locally para CR equivalent to a canonical, to big perhaps, para CR structure of some nth order ODE. Okay, so that's the question, and immediate answer is of course not. No, because just see here that d lambda which lambda is not equal to 0, and this condition is invariant under my transformation. So being 0 or not being 0 is an invariant of my transformation. So definitely para CR, so para 1, 1, n minus 1 type para CR for which this condition is not satisfied cannot come from nth order ODE. So there is no because of this. You can say, okay, there are more no's because you can see that here you have this. It's identically equal 0, right? And it's again a condition that is para CR invariant. But actually, para CR guys of type 1, 1, n minus 1 always satisfy this condition because of my integrability, or because of this form here, right? So this is not an obstacle. So now the question is, can I find some other obstacles for para CR of 1, 1, n minus 1 that prevent such guys to come from ODEs? Okay. So let me give some intuitions. How much time do I have? 10 minutes. Tough. So low dimensions. So low dimensions, so the lowest is just 1, 1, 1, right? So in low dimensions, so the question is if every para CR of type 1, 1, 1 for which this is satisfied comes from ODE modulo contact transformation. So the answer is yes. So I assume that my d lambda, which lambda is not equal 0, then I use this representation, and I can represent my lambda to be dy minus p dx, my mu to be dx by this thing here, or by the comment here. So I can represent my lambda and mu by this, and because of this condition, then I have d lambda, which is not equal 0, I get that dx, dy, dp is not equal 0, therefore actually this function p can be considered next coordinate on this three-dimensional manifold. So then I can have x, y, and p now as coordinates here, and having this as coordinates, I just write mu as the most general form in terms of these coordinates, which is something like a dx plus b dy plus c dp. And now because my mu is given modulo addition of some lambda, I can get rid of this term, and because I can scale, and this thing cannot be 0, I can write it as dp minus some function q of my coordinates x, y, p dx, and then I will define equation q, x, y, y prime. So here this example shows that 1, 1, 1 para CR, which satisfies this condition, always comes from second order ODE modulo contact transformation. So what about next in the row? So next in the row will be 1, 1, 2, which should which I would like to associate with some third order ODE. How can I do this, and is it possible or not? So again, I assume that d lambda, which lambda is not equal 0, I can use my representation here, in which lambda is dy minus p dx, mu is just dx, mu1 is dA1, and mu2 is dA2. And now the question is if I am able to write it, to use my transformation in such a way and change coordinate system in such a way that I put it in the canonical form. So this is not that easy, but this condition tells me again that dx, dy, dp is not equal 0, which means that the function p, which is a function of x, y, or all coordinates a2, have to have either dp over dA1 not equal 0 or dp over dA2 not equal 0. Right? So this condition tells me that. Right? So now I can without loss of generality say that it is this condition that is satisfied. So if this condition is satisfied, then I can solve this thing. Let me call this y1. I can solve this for a1. So I solve this for a1, and I get a1 as a function of x, y, y1, and a2. So now my lambda after this procedure will be as it was. My mu will be as it was, but my mu1 will be now dA1 dx plus dA1 dy plus dA1 dy1 dy1 plus dA1 dA2 times dA2. And now because of my transformations I can add whatever multiple of nu2, but nu2 is proportional to dA, so I can just get rid of this term. I can just use my lambda to get rid of this term, replacing this with some other function, and then this thing cannot be 0 because lambda, mu, nu1 are not 0, so therefore at the end of the day I can write mu1 as dy1 minus some new function q, or better y2 dx, where y2 now is minus dA1 over dy1 to the minus 1 dA1 dx plus y1 dy1 dy. So in other words, just by, I didn't assume nothing yet, I just considered only this thing, and because of this thing I put my lambda in the form I needed, mu in the form I needed, and actually mu1 in the form I needed, where now the function y2 is a function, so now y2 is a function q of x, y, y1, and I2. And now I will be done, provided that this function really does depend on I2. If this function does depend on A2, I can solve it for A2, insert in here, use my transformations, and I will show that such paraserial structures come from the third order ODE. But if this function doesn't depend on A2, I am stuck. So in such a case, this thing depends only on x, y, and y prime, and it therefore defines a second order ODE, which is just y double prime equal y2 of x, y, y prime, and this paraserial structure has sort of structure of such a way that it is paraserial structure coming from 1, paraserial structure coming from a second order ODE extended by a real line that corresponds to this dA2. So this just explains a bit what can happen in this 1, n minus 1 case. So the next question is, can I find some invariant description of when a 1, 1, 2 guy comes, or what is the abstraction for having this thing in this coordinate system? Okay, so this will be perhaps the last thing I am able to say today. I wanted to say that this language is also good for PDEs, but I have no time to explain this. So let me tell only about ODEs today. So now, if I start with a generic 1, 1, 2 para-CR structure, A1, A2, dx, mu dx, mu1, dA1, and mu2, dA2, then I apply Cartan's equivalent. Number one, I can always assume that dP1 over dA1 is not equal to 0. So I have this, and now I apply Cartan equivalence method for these to construct invariants of such guys. So I consider the most general form in the class, which I strangely enough call theta 0, theta 1, theta 3, which will be just given by A, C1, H11, H12, C2, H21, H22, B, 0, 0, F, 0, 0, 0, 0, and now here will be lambda, mu1, mu2, and mu. So essentially I just, theta 0 represents the most general form lambda, theta 1 the most general mu1, theta 2 the most general mu2, and theta 3 the most general mu. And now I can just calculate what is the derivative of the theta 0 west with theta 0. Now this theta 0 form is sort of geometric form, and I can just calculate this thing. When calculating this thing, I just write something, I obtain something like this, again by means of Mathematica, which is a very good tool, complementary to very much advertised Maple. Minus A over F H12 P1 minus H11 P2 H12 H21 minus H11 H22 theta 0 theta 2 theta 3. Now I can just look that I can just kill, so my invariant form theta 0 has the following differential, and I can just, looking at this, I can say, okay, I can just kill this term by choosing appropriately A, and I can make this term to be 1 by choosing appropriately H12. So the thing is that I can make the following normalization now. P1 is just dP over dA1, H12 to the H11 P1 over P1, and this brings me the form d theta 0 to a form like there's some 1 from omega 1, theta 0 plus theta 3, theta 1. After obtaining this normalization, I can just calculate, I'm just finishing, that's just 1 minute more. I can just calculate d theta 1 west with theta 0, theta 1, so I just normalize like this, I recalculate my thetas, I calculate this thing, and then I discover that it has the form of some function I, H11, F, P1, H22, P1 minus H21, P1, and here is theta 0, theta 1, theta 2, theta 3, where this function I is only defined in terms of P and its derivatives, and it is the form like P x2 plus P py2 minus P2 px1 plus P py1. And now if we look at this thing, I just see that there is no way of normalizing anymore if this thing vanishes. So vanishing or not of this thing is a para-CR property. And actually, if I just calculate this J for this structure that was just coming from second order ODE, I see that it is just the case, but if it comes from general third order ODE, it is not the case. So actually vanishing of this or not, non-vanishing of this is abstraction for this para-CR to come from third order ODE, and it turns out that it's just actually the only one you need for a para-CR structure of 1, 1, 2 to come from the third order ODE modulo point transformations. I wanted to make advertisement about the thing for PDEs, but I have no time. The last word I wanted to say is that this, what I was presenting here, is a joint work with Benson, Hill. Okay, thank you very much.